Okay, thank you. I can go ahead now?
Yes, sir.
Oh, thank you very much, madam. So, my talk will concentrate on electric vehicle technology, that is electric propulsion system mainly. What is electrical propulsion system? What are the components of electrical propulsion system? And what are the new technologies being introduced in electrical propulsion system? So in the end, I'll also try to touch upon the vehicle to grid and grid to vehicle concept. During this entire talk, please feel free to interrupt me, have a discussion about any topic you want, any doubts you want to solve. I'll be happy to have an interactive session. So in the series one of this program concentrates on electric vehicle design, its application and control strategies. In my talk, I will concentrate more on electric vehicle design, what all different components are there, and most importantly, the control strategies. Whenever we are talking about any topic, why should we discuss about it, a topic? What is the relevance of that topic? That is the most important question that comes to our mind. Our motivation should be, we will never like to discuss in deep depth about DC motors because they don't have much future. But we want to talk about which is something relevant, which has a standing in the future, and most importantly, it has impact on our day-to-day lives. So why are we discussing about EV? The answer is present global scenario. Let's have a look at the present global scenario. As per UN data, the global population will cross about 9 billion by 2023. This will result in humongous electrical energy demand. In 2012, we globally consumed 20,000 trillion watt hour of energy. That is roughly about energy produced by 200 nuclear power plants. Increased energy demand would be met by increased energy generation. And about 60 to 80% of global warming is due to generation of electrical energy, its usage, and vehicular emissions. Right? If we can recall, many of us, our grandparents didn't need fan that much. We required fan. And the present generation, like my daughter who is 3-4 years old, she requires AC. So first thing she asked me, school, while going to school, does this new school have AC or not in the class? So that is their main concern. So our standard of living is improving constantly, right? And this requires more and more electrical gadgets and more and more electrical energy. So we are consuming more and more energy. Okay. So about 60 to 80% of global warming is due to the generation and usage of electrical energy and vehicular emissions. What is the result of all this? Result of all this is ocean acidification. That means, let's say around 2050, we may not be able to enjoy the beaches as we do now because the water will become too acidic. Extreme weathers, where there are droughts, there will be floods. Where in deserts, there will be snowfalls. Like Saudi Arabia had a lot of flood around 2014. There was a snowfall in Sahara as well as in Abu Dhabi in 2012. Not very long, but at least it was there for 5-10 minutes. Tornadoes, US is having a lot of problems with this, and increased sea levels. Recently, Maldives government conducted their first parliamentary session underwater. Right? The reason was they wanted to tell the world that we are drowning, the water levels are increasing, the islands will not be there, so we have to stay underwater. That's what they wanted to convey by this. There will be shortage of food and water. It is said that the next world war might be fought on over water. And the coral and ecosystems will be permanently damaged. So how to avoid this? What we have to do so that we are able to enjoy the earth as we did during our childhood, and we are able to pass it on the same experience to the next generation. We need to install about 1 million 2 megawatt wind turbines. That is about 300 times the current capacity. We need to have globally 3000 gigawatt peak of solar power. That is again 200 times of current capacity. We need to install 700 gigawatt of nuclear power plants. Considering each nuclear power plant is of 1 gigawatt, we need about 700 nuclear power plants. Think about Chernobyl, right? What happened? Think about the security involved. And the latest example, the Fukushima reactor disaster in Japan. What all problems are associated with this? We need to cut our carbon emissions by 1/4, and we need to increase our fuel economy. This is the main aspect, increasing the fuel economy. In short, we have to do 300 times of what we have done in last 20 years. So by in next 30 years, that means till 2050, we have to do 300 times of what we have done in last 20 years. So this is the biggest challenge we have, that we need technological revolution or the academicians, the researchers, the industrialists, they need to see to it that the technological development is about 300 times of what we have done in last 20 years. Why we have to do this? To ensure sustenance of life as we are living today for the future generation. Otherwise, the earth may become inhabitable. So what are the solutions for this challenge? Government of India has launched Smart City Mission. In Smart City Mission, there are 11 infrastructure elements. Out of them, 3 I find are very much related to the electrical engineering. And the same 3 somewhat correlation have developed, and the 3 solutions are energy generation without gaseous emissions. This means we have to bring in more and more renewable energy based generation, more and more solar and wind. Transportation sector has to undergo serious change. We have to have freedom from gaseous emissions. So electric vehicles will play a huge role there. And energy conservation. See, in this era of energy conservation, energy saved is equivalent to energy generated, or I will say energy saved is energy generated. So we need to bring in more and more smart grids, power quality enhancement we need to bring in, and energy efficient components. All these 5 components what I have listed: renewable energy based generation, electric vehicles, smart grids, power quality, energy efficient components, all these are correlated in electric vehicle. This will become a cycle which will be more clear by the end of the session. So coming to electric vehicle, let's see what is vehicle. A vehicle is a device intended for transportation of any living or non-living entity from one place to another. So we have to carry any living person or a non-living entity from one place to another. But when we are doing this, we have to think about that there should be no damage sustained to the device, the entity, whether it's living or non-living. So our comfort and our safety is of prime importance here. There are many vehicles. We have seen vehicles since ancient ages, whether it's animal-driven carts or boats. We have seen bicycles, cars, ships, and now we are graduated to trucks and helicopters and such spaceships. So whenever you talk about electric vehicle, first thing comes into mind is locomotion. Locomotion involves displacement of living or non-living entity from one place to another. The displacement of land has to have minimum position. That means there should be minimum friction in our design. And the motion should be controlled. This is the most important parameter. Suppose if I have to stop after 100 meters, it should stop after 100 meters. Not before that, not after that. And how we derive the kinetic energy required for motion, that will be the important aspect of a locomotion. So generally we are using petrol and diesel. Previously we had steam engines, so coal was being utilized. And now we are shifting towards electricity. So e-mobility, right? E-mobility is a part of smart city. E-mobility deals with electric vehicles mainly. What is e-mobility? As per the German government and the National Development Plan for Electric Mobility, e-mobility comprises of all street vehicles that are powered by an electric motor. That means all electric vehicles will come under this. The thing is, you cannot have a diesel generator powering an electric motor. You need to have the electric vehicles must get their energy from the power grid. Whether it's battery or any other source, you need to charge it, store the energy, and use it for the locomotion. That is what the e-mobility states. E-mobility will involve power electronics, electrical machines and drives. Power electronics is the main component here because it's going to control the flow of energy. Electric power system will have a role to play because suppose if we start charging our electric vehicles, what will be impact on the grid? That is the main study. How to schedule the charging of electric vehicles. That is the main concept that is being researched widely these days. Besides this, electric e-mobility also involves IoT, AI, machine learning. These will be involved. Data optimization, communication protocols. Before lockdown, I was having a talk with a startup which is dealing in EVs, and we were discussing about how they plan to bring in their new products. So they wanted to have an EV where they will have a system which will say, okay, this is the battery charge, this much distance, you have to log in like a GPS that I want to travel to this location and I am currently at this location. So it will tell, okay, now you take this way. It has less traffic from GPS. And this way is better because you'll be able to reach not only faster, but how your battery will be consumed. That is what it will check. And it will take your driving pattern based on some AI. It will have some data which needs to be optimized because there will be huge data different users are using. So Data optimization will be required. You'll be communicating continuously with the cloud where the data is stored. AI and machine learning will predict what type of driver you are, how you drive the vehicle generally. In this certain situation, how are you going to manage that? So how to optimize your battery charge, how to travel the maximum distance for the given charge. So that is what this new IoT, AI, machine learning, data optimization, communication protocol will play a huge role. In terms of power electronics, if we talk, you must be aware that now we are shifting from silicon-based device to silicon carbide and gallium arsenide or GAP-based devices. They are wide bandgap devices. So main problem in automotive electronics was the temperature. Right? Even though irrespective of the outside temperature, the motor temperature and power electronic converter temperature is going too high. That was the reason of the failure of power converters. Now with these wide bandgap devices, we can not only go for higher switching frequencies, which uses better control, but also we'll have lower switching losses, lower heating of the power electronic system, and it can sustain for higher temperature range. That is the new development that has come about, wide bandgap based power electronic switches. It is silicon carbide or gallium arsenide. So this is an area which needs to be targeted. Those who want to publish papers, this is the area you can target. What is the how we can analyze the operation of inverter with a gallium arsenide and a silicon carbide? How much cost increment will be there and how we will be able to extract the cost? Just to give an example, roughly 100 ampere 150 volt dual pack IGBT will roughly cost about 2,500 at the max. But when you go for gallium arsenide, one switch itself will cost you about, or silicon carbide, one switch of the same rating will be coming nearly at 5,000 to 7,000 rupees. So that's the difference. And undoubtedly our standard silicon based technology is far more mature. That means we have made mistakes and we know how to solve them. So technology is pretty much mature, but in this it's still coming up. But that should not stop us from utilizing it more, right? That should not stop us from exploring the wide bandgap power electronic switches as well as power converters. So what is significance of e-mobility? One is its first and prime importance is environment, right? And performance. This is more efficient compared to your internal combustion based engine based vehicles. The efficiency here can go as high as 80% or so, depending on the different vehicle designs, while internal combustion engine, it will be well below 50%. So one is energy efficiency. Secondly, because we are utilizing energy more efficiently, there will be less wastage of energy and thus will contribute to pollution reduction. Plus, electric vehicles don't have gaseous emissions. Economy and society, it's going to provide us sustainable transportation. In terms of economy, the new EV market will come up. It will provide us more opportunities to develop our economy in terms of providing more jobs, right? And more it will be an intelligence-based economy or a research-based economy, what we say. New startups needs to come up, new models needs to come up. Like someone will say, I'll have battery swapping techniques. Someone has battery charging or fast charging techniques. Other ones have the startup which I was talking about, they were talking about portable EV chargers. Right, you call them, I'm stuck here, they'll come and charge in 5 minutes, something like that. Technology and infrastructure, huge scope for research, huge scope for infrastructure development in terms of charging infrastructure, in terms of V2G, G2V, how will we handle this system, how will be the EV battery charging scheduling will be done. So data handling, communication, optimization, IoT, ANN, all these will play a role. So I was just going today morning through Quora and other websites to see what is happening, and I found out in Norway, if you have an electric vehicle, you get free public parking. There is if you are on an island and you have to ferry across the stream, you have free ferry. There is no toll booth. You don't have to pay any toll tax, and you can even drive in bus lanes. Ahmedabad, the municipality has introduced electric buses currently. There is also in 2019 budget in India, we had incentives for using EVs. To boost EV, I was looking at Insight on India.com and they are saying that we are trying to push the demand by there will be permits. There will be no permit for electric vehicles. You don't need any permit if you want to have public transport, taxis or auto rickshaws, right? Induction of certain percentage of EVs we will have. We will allow leasing of EVs to transport operators. will give higher depreciation. The lending of our EV, the interest rates will be lower, right? The We'll set up the standard so that this much certain fuel efficiency should be there. This will force the automakers as well as the users to go more towards EV. Then there'll be incentives in using EV in terms of tax benefits are there. We'll create an ecosystem like preferential treatment for EVs on road, like what Norway has. We can run bus lanes as well. Right? We need to see one of the biggest challenges in EVs is infrastructure, the charging infrastructure. We have so many petrol stations or diesel stations, but EV stations are very few. We need to build up this infrastructure. How to charge an EV at our home, the scheduling will play a role. So all these new things are coming up. And there is a global fuel economy initiative. They had published a report very recently on vehicle efficiency and electrification, a global status report. So this report talks about fuel economy improvements, what happened from 2010 to 2020, policy progress, fuel economy standards. It talks about country and regional fuel economy policy reviews. It reviews the policy in different countries and regions. And it talks about the global transitions to EVs. And it has set some targets. Let's have a look at targets, what they have set. So in this report, they have set different targets that passenger light duty vehicles, right? So double global economy of new vehicles by 2030, double the global fuel economy, reduce CO2 emissions, and CO2 emissions by 90% by 2050. This is the target they have set. For heavy duty vehicles, it is about 70% carbon emission reduction. For transits, they have said, okay, CO2 reduction by 2035 should be 65%. By 2050, it should be 95%. Right? For two-wheelers and three-wheelers, it's more stringent. By 2035, we need to reduce CO2 emissions by 80%, and 2050, it should be reduced by 90%, 95%. So why e-mobility? Why we want to have electric vehicles? What is significance? One is environmental concern. We want to hand over the environment to the next generation as we have enjoyed it. For this, a cleaner alternative is required. So electric vehicle provides cleaner alternative, cost effective in terms of how much money is spent on charging the battery and driving. That way it's cost effective. And see, most of our gasoline or petrol and diesel comes from the countries like Gulf countries, Nigeria, then other big producers are Nigeria, Libya, Venezuela. Venezuela and Nigeria and Libya, we know what is the situation there. In Arab countries also, the condition is volatile after Arab Spring. So if we talk about in terms of the costing of fuel, undoubtedly the cost has reduced, but still the fuel economy is a little bit volatile. And we don't want to spend our money foreign exchange for this. So it will be more cost effective, better performance in terms of being energy efficient and energy independence. We want independence from petrol and diesel. That's the main thing. So what is electric vehicle? We can term electric vehicle as a battery powered vehicle. That is the first thing. It has a battery to power the vehicle. The battery will be charged from the grid. It has an electric motor to provide the power for propulsion or force to propel the vehicle. The motion is controlled by means of power modulation. That means there is a power electronic converter present between the battery and electric motor to control the flow of power from battery to the electric motor. Why we want to control the flow of power? Or modulate the power? Because we want to control the motion. Ideally, electric vehicles are free from fossil fuel technology. So we'll define electric vehicle as a battery powered electric vehicle where the controlled propulsion is obtained by modulation of power being fed by battery to the electric motor. You can add battery interface with the electric motor through a power electronic converter. So if you buy an electric vehicle and start charging it from your socket, is it free from fossil fuel technology? Is the charging of electric vehicle, suppose we have electric vehicle now and we start charging it from our grid, are we talking about zero carbon emissions or emission free system? What is your take on this? Yes or no? Anyone can answer this? It's about their, what do they feel? If we start charging vehicle from our grid, do you feel it is zero emission or not?
No, sir.
Why?
Because ultimately, when you're charging the vehicles from the grid, ultimately we are using somewhere the thermal plants are running, and again the carbon footprints are somewhere or other they have been increasing and set free in the atmosphere, sir.
Great, sir. Absolutely agree with you. The main problem is the thermal power plants are powering our grid. and we are going to charge our battery from the grid, so it's not going to be free from fossil fuel technology. We need to have more and more renewable. That's what I was saying. There are 6 different things, 5 different things, whether it's renewables, whether it's electric vehicle, it's power quality, energy efficient devices, smart grids. So all these are forming a chain now. That's when our renewable needs to come into picture if you want the electric vehicle technology to really help us in reducing our carbon footprints. So types of vehicles, if we try to distinguish the vehicles or classify the vehicles, one is pure electric vehicle, where only source of power is a battery. So you have battery to power the electric vehicle. Only source of torque generation is electric motor that is going to generate the torque to drive the vehicle. There is no role of internal combustion engine. It's totally absent. So there is no role of internal combustion engine means your weight of the vehicle is reduced considerably. Free from gaseous emissions while propulsion. Right? Ideally, it should be free from gaseous emissions while propulsion. We can achieve with this, but not in terms of charging. When we charge, it's not free from gaseous emissions. But while running, yes, it's free from gaseous emissions. When you talk about hybrid electric vehicle, which is more commonly being used, battery is a source of power. You'll have diesel or petrol tank as a source of power as well. Propulsion is due to an electric motor, and propulsion is due to internal combustion engine. So there are 2 things playing a role now. How you utilize the torque generation from both of them, that depends on your drivetrain, whether it's series hybrid electric vehicle or parallel hybrid electric vehicle. But sometime down the line, we need to shift from hybrid to the pure electric vehicle. So these are the types of electric vehicles. So you have full hybrid electric vehicle drive. So here about 25% potential is for reduction in the CO2 emission. So you'll have internal combustion engine, a motor, power electronics, and high voltage battery. So both are going to, motor as well as the IC engine are both going to provide the torque one way or the other. When you talk about plug-in, but see, the battery is not connected to supply. There is no external port here. So what is going to happen? The diesel engine has to have, there'll be a diesel generator to charge the battery. So how to divide the power among these 3? That optimization plays a role here. When you add the term plug-in, that is plug-in hybrid electric vehicle, you have extra socket to charge the battery. So this uses potential for reduction to 50%. How we achieve this 25%? By optimally using our internal combustion engine. That's how we obtain. When you talk about battery electric drive and renewable based charging, or you talk only about the gaseous emissions while running, then it gives 100% CO2 reduction. So you have only motor, you have a power electronic converter, battery, and a socket for charging. Then we have range extenders as well as fuel cell based battery electric vehicles or fuel cell based electric vehicles. I was recently attending a talk of ARAI, and there that session there are people aware of opinion that fuel cells will take over the market in future. Rather than batteries, or concentration should be on fuel cell. So this is another area which is less explored. How to use fuel cell in vehicle, that can be targeted. So different vehicles are there. When we talk about battery electric vehicle, the structure is simple. Your battery feeding an electric motor. If your regenerative braking incorporated, the motor will act as a generator during the braking. So rather than wasting your energy in form of heat and friction, it will fed back to the battery. When you talk about hybrid, you have both IC engine, electric motor, battery, and petrol tank. When you talk about hybrid electric vehicle, plug-in means there's a port. If you remove the term plug-in, there is no port for charging the battery. So there has to be a diesel generator to charge the battery. And in case of fuel cell, you need a hydrogen tank. So what are features of plug-in electric vehicle? Only source of power is a battery. I'm talking about battery operated plug-in electric vehicle. Only source of torque generation is electric motor. No role of internal combustion engine. Free from gaseous emissions while propelling, and it can be plugged into socket for battery charging. Just to give a global market overview, why we should work in this. By 2020, China had a plan to have about 5 million zero-emission electric vehicles flying on the road. By 2030, India and Germany plan to allow only production of zero-emission passenger vehicles. And by 2040, UK plans to ban petrol and diesel-based cars and allow only electric cars to run on the road. So there is a huge scope for research in this area. So why electric vehicles are popular? Increasing fuel prices, that is a trouble for us. Environmental concerns, what we have discussed. And a huge demand for automobiles. Now everyone has a car. Previously, if you see 30-40 years, hardly anyone will have one Bajaj scooter at their home. So now everyone has car at their home. Then legislative incentives, more tax benefits are coming into picture. Government policies are being framed to promote electric vehicles. Zero emission while running, that is what we want. Reduction in fossil fuel dependency and activation of corporate average fuel economy standards. Looking at the technological aspect, one of the biggest thing has been processors with fast computational speed. We have processors that can work in megahertz range and quickly employ algorithms like vector control, voltage oriented control, which will be used for charging, vector control or DTC, which will be used for propulsion control. ICs with really low propagation delays, nanoseconds and even lower than that. Power electronics, we have shifted from silicon based switches to silicon carbide switches. These offer higher switching frequencies, lower switching losses, and can operate at higher operating temperature. These are the benefits that we are having. So having a look at the key components of EV, you have a battery. It can be lead acid or lithium ion. We are shifting from lead acid to lithium ion. Then electric motors are there. Undoubtedly, this is going to be the main traction motor which is going to propel the vehicle. To control the flow of power from lithium ion to electric motor, we have bidirectional DC-DC converter. This will control the charging of the battery during the regenerative braking, and it will control the discharging of the battery during the motor operation. Then you have 6-switch voltage source inverter, which will convert this DC supply into AC supply. It will allow us to control the phase, frequency, and amplitude of the AC supply being provided to the motor. So ultra capacitors also have been reported, because when you suddenly are braking, the ultra capacitor will store the energy quickly, and when you are accelerating, huge energy will be spent. That we'll see in the result section when we discuss. That time ultra capacitor can provide the energy during acceleration. So these are the key components, like thermal cooling system will be there, DC-DC converter will be there, power electronic converter means inverter will be there, there will be traction motor undoubtedly, on-board charging port will be there, auxiliary battery for running other auxiliaries will be there. We have traction battery pack. So in short, battery pack will be there. On-board charging system has to be there. So rather than having a separate charger and connecting, you just put into plug and it starts charging. That's all. So this is how the power flow takes place. See, your energy storage, that will be battery. It will feed the DC-DC converter. So battery will discharge. DC-DC converter will provide the energy link. This motor drive is nothing but an inverter, which will convert that DC power into AC power for motor, and motor will start running. When you go for regenerative braking, the motor will act as a generator. Rather than wasting the energy in friction and heat, that energy will be converted to electrical energy. It will start supplying to the motor drive. Now this motor, which was acting as an inverter, will act as a active power factor correction device or PWM rectifier and control the DC link voltage. This DC power will be in turn used as a DC-DC converter to charge the battery. So that means this DC-DC converter needs to be bidirectional. That is the first step that we have to have. We cannot have unidirectional DC-DC converter. We need to have bidirectional DC-DC converter. Why regenerative braking is so much important? The reason is, when we are driving our vehicle, the biggest challenge that EV market is facing is that, for acceptance, is that the amount of distance that can be traveled per full charge of the battery. So if you want to travel more distance, more batteries are required, more weight is there. More weight means more torque production, a bulkier motor. Again, this becomes a cycle. So rather than that, we will try to utilize each and every aspect to have energy conservation. So regenerative braking is the main thing in this. When we talk about charging, we'll have a utility plug, AC to DC converter. This will be PWM rectifier, which will feed to the DC link. And here we may have some MCB to separate this drive, motor and drive. And then the DC-DC converter of the electric vehicle, that itself can be used for charging. If you don't want this AC to DC converter, your charging port should be connected, motor should be disconnected, and charging port should be connected here somewhere. So that will be used to charge so that will be on-board charger. You just need to plug in, because this inverter can also plus motors and PMDC motors, PMSM, DC motors, PMDC motors. These motors don't need any power electronic circuit. You can directly connect their supply and drive with the help of a starter. New age motors are PM BLDC permanent magnet brushless DC motors, PM synchronous motors. PM stands for permanent magnets, synchronous reluctance motors, switch reluctance motor, doubly salient motors, and stepper motors, and so on. These motors require some inverter or some other power electronic converter between the supply and the motor, so that it can have controlled excitation. The stator winding excitation is based on the position of the rotor. So these are the new age motors or advanced motor. The benefit of this motor is they provide higher efficiency. So these are the motors used in electric vehicle. Front magnet brushless DC motor, they are predominantly used in two-wheeler electric vehicles. Front magnet synchronous motors are used in four-wheeler electric vehicles. Induction motors, Tesla is employing induction motors. So front magnet motors have only problem that the magnets used, that is ND-FEB. China has monopoly over this, and they have stopped or limited the export of the ND-FEB magnets. So now we have to buy motors for them. And this has increased the cost of the front magnets. So this is one of the challenge. That's why there may be a shift towards induction motor, or switch reluctance motors were there, but they are hardly used now. Their usage is very less. And we are shifting towards synchronous reluctance motor. They are same as PMSM motor in construction, but only thing is you have removed the front magnets. So now the reluctance torque plays the main role, hence we call it synchronous reluctance motor. The only problem here is lower torque, so we are shifting from synchronous reluctance motor to PM assisted synchronous reluctance motor, where the volume of PM material will be lesser. So what are the requirements of electric motors for electric vehicle application? It should have high power, high torque, wide speed range. Just to give an example, a hypothetical case, that if we talk about a DC shunt motor, in DC shunt motor, what happens that the speed more or less remains constant. We cannot use a DC shunt motor. We have to go for DC series motor, where there is wide range of operation. Higher efficiency will play a critical role, because you want your motors to be efficient, because they are going to the main propulsion motors. Here, because our battery power is limited, we need to talk more and more about efficiency. Everywhere we need to eliminate losses and increase efficiency. Reliability, motor should be reliable and robust. Reasonable cost, here will the magnet cost is hurting us. Low noise, small size. Just to talk about low noise, when I was working during my postdoc, there was a gathering of people working in EVs from different domains, and I met a person from Europe who was talking about that in Japan or in Europe, they found that there are more accidents because of EV. You think about why EV will cause more accidents?
Hello, sir.
Yes, madam.
You are not audible, sir, properly.
Okay, now I'm audible.
Yes, sir.
Yeah, I just wanted to know, what is your opinion? Why EVs will be responsible for more accidents?
Maybe due to the acceleration issues.
That can be one aspect, but lesser aspect, because our control, that vector control and drive, whatever we have, it can control acceleration very well. Okay, the answer is something funny. Okay, the person with whom I was talking, that industry, they found out that EVs don't make noise, and people were accustomed to hearing noise when like crossing the roads or flying on the roads. So because of that low noise, they were finding that EVs were more responsible for accidents. So what this group was thinking about, to have a special device which will generate the same noise as it is generated by driving the vehicle, while driving an internal combustion engine based vehicle. So some of us may not agree with this. Why to have noise in EV? That was my question also. But what I'm trying to tell you is that how different people are thinking. So the research has no boundary now. People are thinking of more and more differentiation. Smaller size, undoubtedly size has to be smaller. If you check these days in power electronics industry, we have something called IPM, intelligent power modules. So it is just like if you use a IR2110 IC, gate driver IC, something of similar size, an inverter will be there. Inverter, gate driver in such a small size, right? So about the size of your mobile phone, that's all. That much small inverter will gate driver. So we want it to be more and more compact. Plus we are going for solid state batteries, which will be more compact. Just to talk about battery and battery economy, I was attending a Niti Aayog meeting over this, and a session from Niti Aayog over the battery, and there was a open discussion. So one gentleman presented his idea that they are planned to have set up a firm in India which will recycle the batteries. Even when we talk about lithium ion, cobalt is used in these batteries. Cobalt and some other material also specified, which I'm not able to recall now. But he said that cobalt is currently available only in Congo and that region of Africa. And when these industries try to approach their governments that we want to get cobalt, manganese and these things, for next 20 years or next 100 years, and you want to strike a deal now, it was said no. The government said no, you cannot strike, because reason is cobalt is getting, cost is getting very high. So from these batteries, they want to recycle the batteries, take out the cobalt and other material and sell them. So I believe in Uttarakhand such a plant is coming up, where they want to recycle the batteries to extract cobalt, and they're saying that will be more, that will be highly useful and a profitable business. So this is something out of the box thing, something that we may not have explored. Coming back to motors, permanent magnet brushless motor, they're trapezoidal back EMF. They have quasi square wave currents. That means current is, there is 120-degree mode of conduction, what we do in VSI, same thing applies here. They are using neo-boron dynamium ferrite ion magnets. High efficiency 85 to 90%. Only problem is high torque ripple. Because of the commutation in this motor, the torque ripple is going to be high. And this torque ripple will be responsible for energy loss as well as the reducing the life of the bearings. And permanent magnet synchronous motors, if we talk, they have sinusoidal back EMF, sinusoidal currents. They use the same type of magnet. Efficiency, because of the absence of lower torque ripple, the references cite that their efficiency can be low, torque ripple can be as low as 3% if you're able to control it properly. So you get efficiency about 85 to 95%. That's why, that's the reason in a four-wheeler EV application, this motor is predominantly being used. Induction motor, sinusoidal current, no permanent magnet involved. This is the biggest benefit, but efficiency is lower. Switch reluctance motor, doubly salient structure, non-sinusoidal current, no permanent magnet involved. That's the best feature. It works on reluctance principle. Lower efficiency, 83 to 87% it has compared to PMSM. Problem is very high torque ripple, noisy operation. And the biggest challenge is this. See, for induction motor, PMSM or PMBLD, see, your standard 6-switch 3-leg VSI can work. But for this, a special converter is required. When we talked about synchronous reluctance motor, this motor is envisaged to be the traction motor in electric vehicles, because it is singly excited system, synchronous. It works at synchronous speed, it's sinusoidal currents and voltages it needs. No permanent magnets are involved. That's the best thing. Its efficiency is 80 to 88%. Reluctance torque here is equal to developed torque. When you are working on surface mounted permanent magnet synchronous motor, the reluctance torque is very minimal. That is going to hinder our developed torque. Here we are trying to do reverse. We are trying to increase the reluctance torque. Naturally, there will be noisy operation, but the torque produced is low. That to increase the torque, we are going to PM assisted reluctance motor. So one of the aspects to work upon can be the design, the FEM based design of synchronous reluctance motors. That can, I believe, fetch us good amount of publications, as well as developing the control system for PM assisted synchronous reluctance motor. Let's say vector control or direct torque control, something better than that. When you talk about design of electric vehicles, it's divided in two parts: mechanical design and electrical design. Mechanical design involves determination of the tractive effort to propel the vehicle under a given operating condition. So this deals more with the vehicle dynamics. The electrical design talks more about selection of the electric motor based on the torque speed requirement, selection of power converters, selection of battery pack, design of control system and charge discharge controllers. The control system will involve the propulsion system as well as the battery system and protection system. Because electric vehicle, one of the things is it should not give you shock while driving. So how to protect the driver as person sitting inside, that is a big challenge. So torque speed requirement of EV. Let's have a look at the mechanical design of electric vehicle. So the tractive effort is the force required to propel the vehicle. We call it tractive effort. So this tractive effort has to overcome different things. That is rolling road resistance, resistance between the wheel and the road, that it has to overcome. It has to overcome the aerodynamic drag. It has to overcome the mass of the vehicle to propel it. It has to provide the force for the acceleration. So if we look at this, the tractive force Ft required to propel the vehicle and transmit the force to the ground is given something like this. This part, mass into acceleration, plays a huge role, because most of major power will be utilized during accelerating the vehicle. That's why rather than using a battery, now the next state of technology can be using ultra capacitor. They can give fast power during the acceleration. Then if you are going on a gradient, this sine alpha and cos alpha, they will come into picture. Gravity will come into picture. So that also you have to take into consideration. Mu r is your rolling road coefficient of resistance. So whether it's asphalt road, cement road, whether it is sand, whether it is ice, all these matters play a role. That is why skidding of the vehicle takes place. I had attended a discussion with a Canadian person. They were working, he was working in some industry, and they were working on, in Canada, they found that the vehicle starts to skid over ice. So an automated mechanism which will prevent the skidding over the ice. So the vehicle starts to skid, the FT generation changes such that the vehicle comes back on the road. So this is being done to avoid the accidents. And to do the frontal design of the vehicle so that to reduce the impact of the aerodynamic drag. So we have FT, this is tractive force required to propel the vehicle. Based on this FT, we will try to calculate torque. Force into radius our wheel gives you a torque. So we have the torque with us, and the speed of the vehicle can be how much velocity we need in meter per second divided by the radius. This gives us the vehicle, the speed in terms of radian per second. So we have speed and torque. Based on this, we'll select the electric motor. So based on the torque and speed requirement of the EV, we'll select the electric motor. So whenever we talk about electric motor, whether it's induction motor, PMSM, PMBLDC, or synchronous reluctance motor, the drive plays a very important role. Right? The electric drive is the key component for the electric propulsion system. So what is electric drive? Electric drive is a combination of power electronic converters modulating the power being applied across the motor terminal. So whatever power is coming from the battery, you need to control it. Why we need to control it? So that the speed torque characteristics of the motor can be matched with that demanded by the EV. Here EV is our mechanical load. So we have to match the characteristics of the speed torque characteristics of the motor with that of the requirement of the electric vehicle. For this, we require sensor unit to measure various electrical and mechanical quantities for the implementation of the control algorithm. So this is an electric drive. So your supply, that is a battery, your power electronic converter, that is a DC-DC converter inverter, your electric motor, which can be PMSM, induction motor, PMBLDC, or a synchronous reluctance motor. And mechanical load means when you're driving on the vehicle, how much force opposition is there and what you need to overcome. See, power electronic converter basically consists of power electronic switches, which are dummy in a sense that you need to give them a signal. Okay, now conduct, now stop conducting. So that signals come from a controller. And this controller, what it does, it implements a control system. Control system for controlling the battery discharge, controlling the speed and torque of the motor. How you control both of these things? By controlling the gate pulses. So we need to know the exact condition now to generate the control signal. The control signal is the gate pulses for the power electronic converter. So sensor units have been incorporated. You have current sensor, voltage sensor, you have temperature sensor, speed sensor, different sensors are there. So what is the general structure of a electric drive? So general structure, control structure I'm talking about is something like this. We have speed controller and we have current controller. So first we compare the speed, reference speed with the actual speed. In case of electric vehicle, reference speed will be generated by the driver. The driving profile, how he is driving, that will generate the reference speed. So based on the reference speed, you will compare with the actual speed. The speed control will process the difference between the two and try to generate a reference current such that these two speeds match. Okay, we have usually the formula T minus TL, developed torque minus load torque is equal to J d omega by dt. So if you want to increase the speed, your developed torque has, if you want to accelerate, the developed torque has to be greater than the load torque. And if you want to decelerate, the developed torque has to be lower than the load torque. And if you want to draw at constant speed, that both the torque should be equal. That is the same fundamental principle being used in this. But how we correlate with reference current? The reason is torque is proportional to current in all motors. So we are considering the current. The reason is torque sensors are pretty costly. If you go to buy LEM current sensor at the max with the evaluation board, you will get it as 5,000 rupees. Right? But if you talk about torque sensor, it will be very costly, more than 3 times the cost of this. So that's why we go with current sensors. And it gives good enough control for us. So we have reference current. So this much current should be drawn by the motor so that the requisite torque is developed. If requisite torque is developed, the actual speed will match the reference speed. Again, we'll compare the current, reference current with the actual current, which is sensed by the sensor. Current controller senses this, processes this error and generation of voltage. If you apply this much voltage across motor terminals, then actual current will be equal to reference current. Requisite torque will be developed and the motor will run at reference speed. That means vehicle motion is being controlled. The problem here will be that reference voltage is an analog quantity. whether it is DC or AC, depends on the motor and the control system employed. So this reference voltage cannot be given to the power electronic converter because it is the gate pulses. It requires pulses in digital format. 1 0. 1 means switch turn on, 0 means switch turned off. So use a PWM modulator to convert the analog signal into digital signal. Right? So we will have sensor unit undoubtedly plays a role because it has to provide this signals. So now people are working on fault tolerant control. So one of the problems will be failure in sensors. Suppose you are driving and a speed sensor fails. This entire system is bound to fail. So you need to have sensorless control, which will detect, okay, sensor has failed. Controller will sense, okay, sensor has failed. It will generate a signal for you on your dashboard, sensor has speed, sensor failure. It will shift from sensor-based control to sensorless control. Same way for current control, right? That we have to shift from sensor-based operation to sensorless operation. So that time your Kalman filter, your sliding mode observer, your high frequency signal injection techniques, all these techniques will come into picture to sense the speed or current without the help of any sensor. So if we talk about control of induction motor, we have scalar control, field-oriented control, vector control, direct torque control. Scalar control is coupled control. If you can recall the equivalent circuit of induction motor, if I change the stator voltage, the magnetizing current IM and the current flowing in the other branch, which is responsible for torque production, that will change. Both will change. So this is always sluggish because current through the magnetizing component will change sluggish because the high inductance factor coming into picture. So we want fast dynamic response. So we go to field oriented control. So this is decoupled control. That means you can divide the current into two parts. One is torque producing component of current, other one is flux producing component of current, and you can control both of them separately. In this field oriented control or vector control, you are indirectly controlling torque and flux. How you are indirectly controlling? Because you are assuming that there is a torque producing component of current flowing through the rotor circuit, and there is a magnetizing component of current which is responsible for flux production. It provides fast dynamic response and good steady state response. Then direct torque control was reported in 1987 or 86 in this times. Is a type of scalar control. So this technique says that, okay, you are assuming that this component of current is proportional to torque, but there are many non-linearities coming into picture, like saturation, harmonics, and these things. Why not control torque and flux directly? This gives best transient response. But problem is this involves your hysteresis controllers, which are responsible for torque ripples. So in order to eliminate the torque ripple, again new algorithm has to be introduced. Then there is again space vector direct torque control. But if you employ this, then this switching table goes out of picture. So then there is again a question whether there is a direct torque control or not. So that's why still field oriented control is being used. Again, I agree to the fact that there is a huge debate among the industry persons, academicians, researchers, that which is the best technique. If you check, there is at least I did not find any paper which conclusively says. During one of my talks I was discussing about these control techniques, and one of a faculty colleague who was attending, he asked me that his PhD was on this topic only, and he was facing some issues. So I suggested him that you can divert your PhD work to this area, to concentrate on comparison, actual quantitative comparison of field oriented control and direct torque control on PMSM and induction motor, what results it gives. Then we'll have clear-cut idea of which system is better. So this is the area which can be concentrated upon. So let's have a look of vector control. I am more of this vector control group. I think this is a better technique, but I will be happy if some of you can come up with and refute my thought, and we can shift to direct torque control. The theory of vector control is not new. It's developed in 1970s and commercialized by 1980s. The reason was we needed fast acting power electronic switches. IGBTs provided that, and fast processors. So we are yet to come up with a technique better than vector control. That's why we are still calling it latest technique. Direct torque control has been developed, but it suffers from problem of high torque ripple. And there's flux estimation in DTC. That flux estimation is again has issues. You cannot simply do V minus IR integral of that, because that will bring drift and all these problems come. Drift as well as DC components come into picture. So those who work in signal processing, they can only think about how to estimate flux in the best possible manner with minimum computational time, because that is important. You have many computations. Your processor is going to do many things. You will apply vector control. It is going to in EV apply the battery controller. Plus, it has to scan all peripherals, all sensors. It has to check whether the sensor is failure is there or not. It has to implement software protection. It has own communication protocols and some pins it has to scan. Some wait cycles are involved. So your execution time of the algorithm should be minimum. So still research is going on in the area of vector control. So just to give you a brief about vector control, let's think about this. We came from DC motor to induction motor because of better efficiency of the induction motor and numerous advantages over DC machines. So if I talk about separately excited DC motor, it has the best speed torque characteristics. Torque is proportional to phi A. You play with field current, phi changes. You play with armature voltage, IA changes. So change in armature voltage does not affects armature current only and results in change in developed torque. Change in field voltage affects field flux only and results in change in developed torque. This is perfectly decoupled system, wherein change in field and armature does not affect each other, and we get a good torque control. Now I am talking about paradox. First we said DC induction motors are better than DC motors. Now I'm saying no, this has better speed torque characteristics. So I want my induction motor to have these type of speed torque characteristics. In induction motor, armature current is my current flowing into the rotor, which is responsible for torque production, and IF or the field current is the magnetizing component of current. So we had VBAF control. In VBAF control, we could not separately control these two currents, the torque producing component of current and magnetizing current. So this resulted in poor response. And why we call it scalar control? Because we are controlling only the magnitude of voltage and current. We are talking only about magnitude. So decoupled control was not possible. Initially, we were using this, but with the advent of fast acting power electronic switches, which can work in 20 kilowatts easily, it's available now. We can go till 50 kilowatts switches are there. With silicon carbide switches, we can go still higher. And mainly important processors, right? Your DSP processor, your FPGA processor, they can implement the complex control algorithm very fast. FPGA, you can have parallel processing as well. It can make it still faster. So vector control exploits this facility, and it can impart induction motor with the torque speed characteristics of a separately excited DC motor. In vector control, also known as field-oriented control, we try to control the magnitude of phase, frequency, and amplitude. Phase, frequency, and amplitude of stator voltage and current. So heart of vector control is ABC to DQ0 transformation. You can call it as Clark to Park transformation as well. So this is what ABC to DQ0 transformation is all about. You have VA, VB, VC. These are the three voltage. It can be flux, it can be current. Right? These are three balanced quantities. Because our motor will always require balanced currents. That's why I'm talking about balanced quantities. So these three balanced quantities are fed to this block, ABC to DQ0 transform. I get output as D and Q. Okay, VD, VQ. And another input is theta. This is my rotor position. What is the position of the rotor? So, or in our case, if you talk about induction motor, what is the position of the stator flux? So theta. So I have three inputs, VA, VB, VC, or IA, IB, IC, and the fourth input is theta. This is the I need to measure. These also I need to have. Then my output is VD and VQ. This is very simple. So if we talk about this VD and VQ, this is just a mathematical equation. See here, it's just a mathematical equation. But why are we doing this? What is the benefit of having VD and VQ? So VD or ID will represent the flux producing component of current, and VQ will represent the torque producing component. More than that, the thing is these three are sinusoidal quantities. That means these are AC quantities. These two are DC quantities. Okay, that is the most important parameter. These two are DQ or DC quantities. So going to vector control, D axis current represents flux producing component of current. Q axis current represents torque producing component of current. So with ABC to DQ0 transformation, we are going to resolve the three-phase AC currents IA, IB, IC into two DC quantities D and Q. So vector control uses ABC to DQ0 transformation for transforming three-phase AC stator currents into DC DQ currents. So see, in any control, we are going to control three currents, A, B, C, and AC quantities. AC quantity has phase, frequency, and amplitude. Because we are converting to DC, first thing we have to control two quantities, D and Q, and only magnitude, because now frequency and phase are out of picture. So this makes my control system easier. D axis current is flux producing component of current. Q axis current is torque producing component of current. D axis current is in phase with the rotor flux. Q axis current is in quadrature with the rotor flux. That's why we call it Q axis. D axis current is analogous to field current of separately excited DC motor. Q axis current is analogous to armature current of the separately excited DC motor. So only thing when we do vector control, we have to take care that the two currents are at 90 degree to each other. If they are not, your vector control will be totally a failure. So this your control system, if you're applying properly, this will be maintained. So change in D axis current does not affect Q axis current and vice versa. So for constant D axis current representing flux, the torque developed by the induction motor is proportional to Q axis current. See, our induction motor, if I talk about, we will talk about PMSM as well. But first, if I talk about induction motor or any motor, is designed to operate at knee point of magnetization curve. If you go above this point, saturation will occur. So we don't want to operate in this region. And if you go below this, that is underutilization of the machine. Mainly, you are the tooth of the stator slot is having the lowest area, and we have fixed our maximum flux density. So your tooth is designed such that in spite of the maximum flux density, it will not saturate. If you are reducing your flux density, then that much bigger tooth was not required. Your more material is used. That is underutilization of the machine. Machine could have been far cheaper. So that's why we'll operate our motor at the required magnetization. So our flux producing component is going to be constant. So this is the vector control. I will try to explain this block diagram and working, whatever we have done, how it is implemented. Please feel free to ask me questions anytime during this. So this is my inverter. 1, 2, 3, 4, 5, 6 switches and 3 legs. Leg 1, leg 2, leg 3. They are being provided gate pulse. I have taken this from PSIM. I am using PSIM more these days. So these are the gate pulses Q1, Q3, Q5. This is for Q1, Q3, Q5. The knot of this is for lower switches because we are operating in 180 degree mode of conduction, you can see. So one upper switch on, two lower switch on, or two upper switch on and one lower switch on. This is our mode of conduction. So if upper switch is on, lower switch is off, that's why I put a NOT gate. If you're applying this in practical, you have to keep a dead time. Dead time means once this switch is on and you want to turn it off, then turn it on, then give some small time, let's say 4 microseconds. Why? Because in simulation fine, your switch can turn off immediately. But in actual practice, there's a turn off time. Switch will take finite amount of time to turn off. This fellow, if it turns on, when this fellow is trying to turn off, then there will be dead short circuit across the battery. Your battery will discharge very fast and it will be damaged. So your dead time, that means 4 microseconds, no gate pulse is applied when you are transitioning from this switch to this switch. If you buy a gate driver card these days, some high-end gate driver card, then they have inbuilt dead time control. So you have to just give the pulses and it will generate the dead time by itself. That is another benefit of the gate driver circuit that we are having. So, but remember, if you have dead time, then it is going to reduce the value of voltage and it is going to create some distortions as well. This is the problem. On the one hand, dead time will protect the short circuiting of inverter leg, but on the other hand, it will cause instability. It reduces their voltage, it causes distortion. So this inverter is feeding this induction motor connected to load. I have programmed this load to behave as a electric vehicle. That FT formula what we had discussed before, I have incorporated that as a torque for this. I am sensing three currents. Okay, stator currents are sensed. Many times I have seen in practice in hardware implementation, it picks up noise, high frequency noise. So I have kept low pass filters, and these low pass filters are operating at 5000 Hertz switching frequency. They can remove the noise, and that is applied to the ABC to DQ0 transformation. So I will get this onward, this point onwards, your control system starts. So this is a part of your DSP code. So you have got ABC to DQ transform, the mathematical two equations we discussed, and I'll get ID and IQ. These are the DC quantities. So from 3 AC quantities, which required control of phase, frequency, and amplitude, I have now 2 DC quantities, so only 2 quantities will be controlled. Plus, instead of phase, frequency, and amplitude, I have to control only and only the amplitude or magnitude. It also requires fourth input theta. We'll check at the end how theta was found out. There is one more sensor, that is speed. I'm sensing the speed. So the structure comprises of outer speed loop, that is here, inner D axis current loop, that is here, and inner Q axis current loop, that is here. See, current loop will work on electrical time constant, which is slower. That's why it's inner loop. It works faster. This works on mechanical time constant. That's why it's outer loop. It takes more time to operate. So first, this measured speed is compared with the commanded value. So commanded value comes from the driver command, how you're accelerating, what is the type of road based on that. So one commanded value will be generated. That will be compared with the actual speed. So resulting speed error is fed to a PI controller. PI controller processes this error and tells, okay, this much torque should be maintained so that the reference speed matches with the commanded value. Again, we are not using torque sensor, so we have said that if you maintain this current, this is ID command is my D-axis current command for magnetizing component. If I maintain this current constant, we have to keep our magnetizing component constant, right? If you're not operating field weakening region, this has to be kept constant. Then my torque is proportional to the Q-axis current. So this output reference torque represents Q-axis current. I have kept a limiter, but if your control system is working absolutely fine, there will be no need for limiter. This is just for protection purpose, so that the current does not exceed the rated value. So I got a reference value of current. Now this current, actual IQ current and reference current are compared. Resulting error is processed by a PI controller. Output of the PI controller is VQ current. If you maintain this much DC voltage, then this much current will be drawn. If this much current is drawn, the required torque is developed. So the two speeds, commanded and actual speed, will match. So our proper motion is there. In induction motor also, magnetizing component plays a role. So we have the magnetizing no load magnetizing current here. That is equivalent to a no load current. I have kept that as a reference. I am comparing with the actual D-axis current I obtained here by resolving the ABC currents into DQ currents. So actual D current and reference or commanded D current are compared. Resulting error is again processed by a PI controller. PI controller, this much D-axis voltage, DC D-axis voltage should be maintained across the motor so that these two current match. It is important for these two current to match so that we are operating at the knee point of magnetization curve. Now, these two VD and VQ are the DC voltages. Our motor talks about AC voltages. So we'll convert this DC voltages into AC voltages. This was ABC to DQ. We'll do inverse transformation, DQ to ABC. So I got ABC voltages. So this much voltage need to be applied across the stator terminals so that required current is developed, required torque is developed, and the motor runs at required speed. Again, these are three analog signals. Inverter talks about this digital signals. So I need to convert analog to digital by means of a PWM sinusoidal pulse width modulation I use, but you can use space vector modulation as well. So here are two for computational simplicity. I use sinusoidal pulse width modulation. These days in DSP processor, you need not compute because I already had a written code. I'm still following that old technique, but these days in DSP, you are just a register and you have to keep, suppose a bit is put 1, it will act as SPWM, bit is 0, it will act as SV, space vector modulation. So you just need to generate these three signals and give it to the designated register and it will do set the bits, it will do this by itself. So that is the easier for us. So here the sinusoidal currents are compared with the triangular currents, triangular carrier signals which are having high frequency. So how now to go about this theta? That is the question. So I have my reference speed here, that is the rotor speed. I will convert my rotor speed to rotor speed electrical from mechanical to electrical. Then what I will do, this IQ, this is, but I am going to control currents which are going to rotate at the frequency of the current is same as the supply frequency, that is synchronous frequency. So what I will try, how to find out synchronous frequency? That means how to find out the synchronous speed. First I have got rotor speed. I will convert into electrical. Then I will rotor speed plus slip speed. This omega 2 is my slip speed. So rotor speed plus slip speed gives me omega 1. That is my synchronous speed. So how to find out this omega 2? So this is the formula for that. 1 by TR, that is rotor time constant, into ISQ, that is the commanded value, divided by ISD, that is again the command. These two values are known to us. Based on this, you will try to find out. Okay. So this is your slip speed. Slip speed plus your rotor speed gives you synchronous speed. Integral of synchronous speed gives you rotor position. So this is the crux of vector control. Any suggestions or doubts or any points of discussions you have, please let me know.
Sir, I have a query.
Yeah, please.
Can you please repeat how the command value of D-axis current is decided? And secondly, how do we find out the PI controller constants?
Okay, great. Thank you for asking this.
Thank you.
D-axis current is ensures your magnetizing current. See, your motor is going to operate in two regions. One is from 0 to base speed. Another one is above base speed. That is field weakening region. I've been talking only in the base region, okay, below the base speed. So what I do, this current is my magnetizing current. how to find the magnetizing current of the motor. When I was simulating during my PhD, I found this a huge difficulty, how to find out, because I think I was not applying my logic. I was just going to different manuals and literature and trying to find out how they decided. The simplest thing is when we do no load test on induction motor, that no load current is a magnetizing current. So this part is approximately the no load current. That is how I find out my commanded value of dx's current. Coming to PI controller, how to tune PI controller, because that is going to be very important aspect, how to tune PI controller. PI has two constants, one is Kp, that is proportional constant, and one is or proportional gain and integral gain. So the method being followed by most of the literature is the Bode plot. You have to model this system. Okay, you have to model this system in DQ. Peter Cross's excellent book for understanding the modeling of this motor. Make a mathematical model, shift it to S domain, then take out the Bode plot. But my only question comes in that is that we need to take many assumptions when we are modeling the motor. Because of this, for me it did not work. For someone else it may have worked. For me it did not work. So how I plan to tune the PI, I have developed an algorithm called GSPI with different integral gain determination. What this algorithm does, it takes the error into account. Okay. Now let's see how a PI behaves. When your error is very high, let's say motor is about to start. So my commanded speed is 1000 and my actual speed is 0. So error will be 1000. So now this 1000 is a huge error. So when you want to reduce a huge error, the Kp, the proportional gain, is responsible for reduction of this error. So Kp should be very high. Why Kp should be very high? Kp into E will give me current. So this current is very large. So I will limit it at a rated current. So my motor will run at rated value, rated current, and it will try to accelerate the motor. What happens during starting? Remember, starting of induction motor. We try to limit the current at starting because huge current are drawn to accelerate the motor. So a motor will accelerate. When the error reduces, what will happen? The Kp into E will be very small to maintain. So that time that integral current comes into picture. That not integral current, the integral gain comes into picture. So what that algorithm does, gain scheduling algorithm, it start incrementing the Ki when you are near the steady state, when the error is reduced. So what it does, it online tuning of Kp and Ki. So Kp and Ki are changed as per the value of error. That is one of the best things you can do. The reason why I'm saying is this, because when we apply the drive in electric vehicle, it is going to have different operating conditions. So those every operating condition we cannot envisage, and that is the limitation when we go with other techniques. So I use the online tuning of PI with the gain scheduling algorithm, where Kp and Ki are changed based on the error input. First. Second, I will suggest is that use of meta heuristic technique, that is GA and PSO, or some Wolf colony optimization. I use PSO more efficiently, since I am more comfortable using PSO because it gave me better result. So what it does, PSO takes this error at the input of PI, processes them, and predicts what should be the value of Kp and Ki. Only challenge here will be not the PSO algorithm. PSO algorithm can be coded in 15 minutes and understood in 15 minutes. That's only half an hour job at the max. But only problem will be the how to make the cost function in this. That will be the challenge for you. So simply, if you do offline tuning, you can use something called IATE method, IET method, those methods. If you are going for online, yes, then it will be a challenging aspect. I hope, sir, I have answered your question. Query? Or any
Yes,
further?
sir. Yes.
Thank you, sir.
Thank you.
Another thing, when you pointed about PI, let me tell you, PI works very well when the input is DC. That means the error is DC. Okay, that is the hidden advantage of this system. Because your error is DC, these two currents are going to be DC quantities. Same way, IQ is also going to be DC quantity, and speed is not going to oscillate. We don't want speed to oscillate, so I'll say DC quantity. PI works well with DC quantity only. PI cannot work with AC quantities. If you want to work with AC quantities, you have to change this from PI to PR controller, that is proportional resonant controller. It involves more amount of gains. So as mentioned, this session of ours, or this program of ours, also includes artificial intelligence. So let me throw some light on where you can use AI techniques. I believe many of the participants are working in AI. Can anyone tell me, according to you, where can AI fit into this? Any of your random guess is fine. It may generate a new idea. Okay, I'll start. Then I hope someone picks up. This low pass filter has a problem of phase shift. You must know, right? It always creates problem of phase shift. So in order to avoid the phase shift and the dynamic response issues, we can remove them, these low pass filters, and replace them with ANN technique called adaptive linear neurons. We can put it adaptive linear neuron. That can be one. Second, computation of sine theta is very difficult for a processor. Let me give an example based on my experience. Once I was working with a student and we were coding, and by mistake in my DSP processor, he put sine bracket theta. Usually we in processors we use IQ format that uses a lookup table, built-in lookup table in math library. So instead of underscore IQ sine theta, he put sine theta, and my coding took me, the execution time of the algorithm increased beyond 20 milliseconds, which was not used because I was using it for a grid-tied inverter. Then I found out this mistake and changes. That much is the impact of sine. So you can also make this, replace this with a ANN based network, which will give, you feed ABC, it gives you DQ. Okay. One more aspect can be PI. How to tune PI? You can replace PI with ANN based controller. It has been done many times. You can see the papers from 2000 to 2010. Many papers are there. Other thing is there now, the new concept is no, PI is better. Now the general concept is PI is better. You can use ANN, like what sir previously told. We can use ANN to tune the PI. That can be used. Online tuning, I said some gain scheduling or PSO. You can use ANN as well. Other aspect of ANN is speed sensors. See, speed sensors in industries, they're bound to fail more compared to others. And sometimes it may happen that in industry, your shaft is not accessible to you, or the motor is deep down. Okay. And motor is 20 feet deep and you have to take a cable from your sensor outside. That is going to cause a lot of problems in terms of picking up noise, in terms of breaking off cable and all these things. So sensorless techniques are there. So you can use ANN to process these currents or the switching signals and predict what is the speed of the motor without sensing. So based on current and volt switching signals, you can say this much is the voltage. That is one aspect. Second most important, if anyone found out, is this 1 by TR. This is rotor time constant. It requires rotor resistance. It requires rotor inductance. But as we know, as the motor runs, and in electric vehicle even more, the temperature rise is going to be issue. So our resistance is going to change over a period of time. So this change in resistor is going to play problem here. TR. If TR is wrong, this estimation is a problematic issue. Your synchronous speed is wrong. Then you can use ANN or machine learning to find out, estimate the accurate value of TR at each sampling instant or after some 100,000 sampling instants. These are the ANN. And if you refer some of the literature, they also developed PWM, means ANN based PWM switching. So this is where ANN come into picture. Someone may say, okay, this has been explored area, but let me tell you, a lot of scope is there. Recently, I met a student from Australia and I'm working with him on how to estimate the speed. And we are using this ID command, and difference between ID and ID command, that means this error and this IQ error to estimate speed. And there he is working in ANN and ML, he's working in this area. So a lot of scope is there, even though you'll find many papers, and it is true that it is saturated area, but there is wider scope. Anyone will like to comment anything about ANN or use of AI or any other technique, ML technique in this? Let's make it more interactive. मला आवडेल जर का आपण थोडं डिस्कशन केलं तर चांगलं राहिले. Okay, going ahead, I'll share you some results. I have reduced the mechanical time constant of the motor so that I can fit the speed in smaller time. Get faster acceleration. See, it starts from 0 and about at 0.15, let's say it attains the reference speed of 1000 RPM. Right? At 0.15, it is attaining the reference speed of 1000 RPM. See the currents. It's 45 ampere. I have kept the limit for current. Current never exceeds 45 ampere. And about 0.15 it drops down. That means at starting the currents are high, fine. See the current frequency of current is also lesser. Here frequency is higher because it is trying to reach from 0 to 1000 speed. That's why frequency is lower. But see, I don't need a starter now. Right? Many times when we are teaching power electronics subject, we teach AC voltage controller, specifically 3-phase AC voltage controller. And we say that, give example that it is used in soft starting of induction motor, but it's not required. Once you use a drive, soft starter is not required. It is going to perform the operation of starter plus it is going to perform the operation of a speed controller. So here the current is changed. So coming to vector control, let's graduate. Okay, I forgot one point. If you are applying the same technique for a permanent magnet synchronous motor, there you have magnets on the rotor. Those magnets are responsible for magnetization of air gap. Those magnets are responsible for magnetization of air gap. So you don't need magnetizing current. So first change will be ID command is 0 because magnets are going to provide. So PMSM does not need this. So ID command will be 0. That is the first thing in control. Second, there is no slip in permanent magnet synchronous motor. So this term 1 by TR, this goes out of pictures. Omega R is equal to omega S. So it's more simple when you work with permanent magnet synchronous motor. So when we talk about electric vehicle, there is one more aspect called electric differential. What does electric differential mean? See, we are using mechanical differential, but again, it's going to be more lossy. So why not go for electric differential? So in electric differential, we try to control the speed of two wheels. Let's say your right wheel and left wheel will try to control the speed. If your left wheel is slower than the right wheel, we'll take a turn left. If your right wheel is slower, we'll take a turn right. So that is called electric differential. This is achieved without the role of any mechanical components. So how we'll achieve this? Usually it is like this: motor, fixed gear, and your differential, mechanical differential. Okay. Here, see, now we have two-wheel drive. That means motor, fixed gear connected to the wheel, or if you have hub motor, that means motor mounted inside the wheel. Two separate motors are there. So if you have two separate motors, you can easily achieve this. If you have two separate motors, you can easily achieve this. So what is the problem involved in using two separate motors? Can anyone guess, or can you present your idea? What is the difference between, what is the problem faced when you have two separate motors?
Coordination of the driving wheels.
Sir, can you please repeat? I was not able to hear you clearly.
Coordination of the driven wheels.
Okay, coordination of driving wheel, I agree with you. So that's where your vector control has to play a role, that both motors should be identical, both tuning should be identical, and both motors should be provided the same amount of stator current. We are talking in terms of phase, frequency, and amplitude. So your control system solves this issue. Okay, but when two motors are there, you agree two inverters will be required?
Yes.
You agree to
Yes,
this
sir.
fact?
Yes,
That
sir.
yeah. If two
Yes,
inverters
sir.
are required, means 12 switches are there, and more gate drivers are needed. So if you compare, like I said, if you want to buy a dual pack IGBT of let's say 100 or 150 ampere, 600 volt, the cost will be around 2,500 rupees. But the driver for this, a standard driver for this, will be 6,500 rupees. So driver cost is very high. So you are increasing the component, power electronic components, you are increasing the analog signal electronic components. All these problems are there. So this is the biggest challenge that we are having. And like sir mentioned ahead, that coordination between the two rotors, how to control the two motors. So what is the solution? So I have worked on a paper called Vector Control of EV based on dual rotor motor. This is a special motor in which there are two rotors. Usually we have only one rotor. You may have extended rotor on both sides, but they run at the same speed. In this, what we have done, we have separated the rotors. There is an inner rotor, stator, outer rotor. So stator is a sandwich between the two rotors. So we have only one stator and two rotors. So this is the control system developed. It is actually vector control only. So this is vector control. If you see, this is the vector control for one wheel. Let's say wheel 1 or motor 1. This is vector control for wheel 2. So this is outer wheel. This is rotor 1 connected to this wheel. This is rotor 2 connected to the other wheel. Other all things remain same. What we have done here, the vector control says that this much voltage is required for controlling the speed of this wheel. Now this vector control says that this much voltage is required for controlling the speed of this wheel. So we have two things. See, outer speed loop for 1, inner Q current loop for 2 for 1, and D axis current loop for 1. This D axis current is 0 because it's a dual rotor PMSM. Because it's a dual rotor PMSM, the magnetizing component is not required. So this is D axis loop. Same way D axis loop for rotor 2, Q axis loop for rotor 2, and speed loop for rotor 2. So I get these values. So here only novelty is how to generate, how to find the resultant of these two different Q voltages and these two different D voltages. That is the first challenge. Second, how to resolve the components like Q axis reference, Q axis current 1, D axis current 1, Q axis current 2, and D axis current 2. So one current has to be resolved into 4 components. That's why I said 3-phase to 4-phase transformation. So this is the 3-phase to 4-phase transformation. First is done is ID and IQ it finds out, that is three-phase to two-phase transformation. Then again ID and IQ are processed by this SCAI matrix to find out ID1, IQ1, ID2, IQ2. So here zeta1 and zeta2 play a role. They are the one who are going to separate out the components into for rotor 1 and rotor 2. So how zeta1 and zeta2 this is this. So we have determined some equation. So we are going to compare the position of the two rotors. Based on then zeta I will be generated. Based on zeta I, we will check what is the flux value for the both the motors, and from this we will generate zeta1. Based on zeta1, zeta2 will be generated. That's how it is being done. So what is we have done? We have converted the three-phase AC currents ABC into four-phase transformation. All these are DC quantities. That's why we are able to control them with a PI controller. So just to tell you how the results work. See, whenever we test a vehicle, suppose one person is testing in his university, second person is in university, or in his road. Each road is different. So we cannot say, okay, this vehicle will behave like this, or its standard is like this, standard efficiency is like. That's why we have something called drive cycle. Drive cycle means you test your vehicle with that profile, speed versus time profile. So this is a vehicle, I have modified this to suit my simulation needs of 60-second time. This is a customized new European driving cycle. So this is the driving cycle. See, here is acceleration, constant speed, deceleration, acceleration, constant speed, deceleration, acceleration, constant speed, deceleration, again constant speed, then deceleration. So you see the torque. This is the torque generated during acceleration, because at m into a, mass into acceleration plays a huge role. That's why torque is very high during the acceleration. Constant speed torque is very low. That's why we can go with field weakening mode. And then here again deceleration, the torque is very high. The torque is negative because the motor is now braking mode. We need to utilize this torque into speed to charge our battery. Same way is occurring here. See here, acceleration, there is a high torque. As the speed increases, little bit increasing torque is there. Constant torque when the motor speed is constant. Negative torque when the deceleration takes place. And this is the profile for acceleration. And see, this is the rotor speed of the vehicle. Okay. Now each wheel is rotating at different speeds. So pink one is the speed of the right wheel, blue one is the speed of the left wheel. So I tried to study the literature and found out that there are some averaging techniques that are employed for different drives. But when I applied that technique for a motor, for our electric vehicle, I found that the two speeds are not exactly equal. What we are controlling? We are controlling the average speed, not the individual speed of the two wheels or two rotors. So this resulted in both the vehicles having different speeds, but average speed is same as per the reference value. Even though the reference speed is being average speed is controlled at reference value, our vehicle will not have proper motion. See this speed is more, blue speed is less here. That means the two will have different speed. That means your vehicle cannot go in linear motion. The vehicle will be like, in the movies they show now, when the vehicle is out of control, it is swirling from one side to the next. It will be like that, and we cannot have that. Same way I tried another technique, same thing it did. The average speed was controlled, but the vehicle motion is not controlled. So the need was to control the two vehicle speed individually rather than controlling the average speed. So that with the three-phase to four-phase transformation, we'll be able to achieve that. So this is the speed profile of the vehicles. This is the vehicle speed. See, this is the speed of the right wheel. You can see here it is flat part, but check here. One wheel is having higher speed, one wheel is having lower speed. This is what was required. See, a difference in speed is there. I wanted the difference in speed to be this. So I'm able to achieve this. If you correlate this with this, see how the vehicle is moving. It's starting at this point, takes a turn, drives a little bit, takes again a turn, drives in linear motion, takes a turn, right? So again drives at constant speed, again takes a turn. So this positive and negative indicate the left side driving and right side zero indicates the linear motion. See, whenever it is constant, it is linear motion. So this is how the vehicle path will be because of the differentials. Why this is? We are controlling the speed of the two wheels separately. That is where the catch is here. This is the stator current. I was getting some spikes when we are changing suddenly. This I need to rectify. Same way torque is there. The thing in dual rotor motor is the two torques are in opposite direction. Dual rotor motors are highly used in this ship propulsion. So one torque is negative, which we cannot have. So we need to have proper gear arrangement to convert that negative torque into positive torque. This is your state of charge. See, state of charge battery is fully charged 100%. You are accelerating. That's why there is a huge fall in state of charge. I'm telling relatively. Then there is a slow decay in charge because the battery is running at constant speed and much power is not required. It is more clear here. I'm talking about this part of the code, last part. Okay, here it started to acceleration is there. Huge power is required to accelerate. That's why state of charge falls down. Then it rotates at then it runs at constant speed. Because it's constant speed, still power is required but less. That's why rate of fall is lesser. Then it decelerates. Deceleration means we are employing the regenerative braking. That means the battery is being charged, so battery will be quickly charged here. Again, it runs at constant speed. Again, there is fall in state of charge. Again, deceleration. Again, charging of the battery pack. This is how SOC varies. And this is the distance traveled, about 275 meters we traveled with this. And this is the vehicle speed. You can see it is as per the drive cycle. Both are matching. And this was when we tested the same scheme on the highway driving cycle. It ran fine. And this is the American driving cycle. We could achieve the control in all the 3 driving cycles. See, there are different driving cycles: American driving cycles, urban European driving cycles, highway driving cycles, city driving cycles. So when you develop your EV, you need to test for different driving cycles. So this is a map of efficiency. Here is where I will require your help. See, the red part indicates that efficiency is very high, near 90%. This yellow, blue part indicates 10%, and other colors are there in between. See, most of the time, whenever I'm accelerating, I need high power. That time I can utilize the motor to the best of its efficiency. Otherwise, the motor efficiency is poor. So we need to develop a control algorithm, either into vector control or somewhere else, or a separate algorithm, new algorithm, which will ensure that my operating point stays in this dark red region and not in yellow, blue, or green region. This is a challenge. So you need to have some energy efficiency, like energy efficient optimization algorithm. So you can use ANN or ML techniques, machine learning techniques, to vary the value of IQ and ID such that my operating point stays in this red region. This is an area that can be targeted for research and publication, as well as for masters and PhD students. So this is what we had discussed, that 3-phase to 4-phase transformation. You have 2 separate vector control techniques, and then you try to again have 3-phase to 4-phase to 3-phase inverse transformation. So you from 4 phases you will get 3 phase. That's how it is working. So when we talk about electric vehicles, it is going to be something like this. You will have a battery will feed to controller. This is DC-DC converter plus inverter and a motor. When you want to charge it, it is going to be grid to rectifier and DC-DC converter. This will make a charger and charge the battery. This is how we are working. When you are going for regenerative braking, motor is going to go through the inverter and charger. Inverter will work as a PWM rectifier, bidirectional DC-DC converter, and charge the battery. So these are the things that are going to be there. So the new thing which I'm going to discuss now is the application of Z source converter. There are 2 converters. One is DC-DC converter. One is your inverter. Whenever we talk about 2 converters, means more number of switches, more driver circuit, more component count, lesser reliability. Another thing, we want to make our circuit more and more compact. You don't want your propulsion system to be a size of a big suitcase and put it there. We don't want that. We want it to be really compact. Swiss company is working on a electric propulsion system. They have put on the website where it is inside the wheel. Inside your wheel, there is a motor, there is a vector control unit, inverter, DC-DC converter, everything. Just battery connection is required. That much compact they are trying to make. What is Z source converter? Other name of Z source converter is a impedance source converter. It combines the buck boost operation, the boost operation or buck operation DC-DC converter mode, and a VSI. See, I had talked about dead time. The benefit of this is no dead time required. You want the short circuit to take place in an inverter leg. That is what you require. There is no need to avoid short circuit. So in normal inverter, you want a short circuit dead time to be there. It causes distortion. Here you don't need a short circuit. There is going to be no distortion. So impedance source converter can perform task of buck and boost without adding dead time. Without dead time, you can achieve this. This makes your gate driver simpler. This makes your PWM circuit simple. It has been used for solar photovoltaic system, wind system, and vehicle. So even if you're working in renewables, you can easily use this converter. And see, the vector control, what we studied for motors, is easily applicable to grid-tied inverters. Whether you're working on UPQC, that is Unified Power Quality Conditioner, shunt active filters, still vector control is there. Just the name is different, voltage oriented control. For wind and solar, we also use voltage oriented control. IDIQ remains same. We there call it reactive power and active power. That's the only difference. So Z source converter can perform this buck and boost as well as it can perform the inverter operation by insertion of shoot through stages. What is shoot through stage, that we'll see. Z source is less affected by short circuit of the legs and the distortion caused by the dead times. There is a special network, 2-port network consisting of 2 inductors and 2 capacitors in shape of X or Z. So this is the Z source inverter, right? This is taken from this reference. So this is your normal inverter, 6-switch inverter. This is your battery, this is your motor. And in between there's this 2 inductors and 2 capacitors. Okay. And this is a diode here to prevent the flow of energy from here back to here. So this is the equivalent circuit. Okay, you have 2 voltage source based on the back EMF here, and this is the battery and this is the Z source. So once you short, there are 2 modes. One, your motor is going to operate. Second thing is this inverter switches will be short circuited. So if inverter switches is short circuited, it will be like this. So energy is stored in the inductor, same as our boost, how our boost converter works. When we turn on the switch, the inductor is short in so current is from battery. I'm talking about boost converter, battery, inductor, switch back to battery. So energy is stored in the inductor. When you open the switch, inductor will oppose the rate of change of current because now load is going to come into picture, current is going to fall. So inductor opposes the rate of change of current, it will try to act as a source and pump the energy. So voltage across load is battery voltage plus inductor voltage. Same thing is happening here. But here your capacitor also comes into picture. Right? So your path can be, let's say, from here to back to charge the capacitor. When it is short circuited, it can be from this. This path is there, right? This path is there. So when these different paths are there. So just to explain you more about shoot through stage, this part, what you are seeing, is your normal PWM. Let's say sinusoidal pulse width modulation. VA, VB, VC are your reference voltages. They are in straight lines. The reason is, see, we are going to employ ZOH, zero order hold. So for 1 frequency cycle or 2 cycles, it is going to be constant. That's how you practically employ based on your sampling frequency. So here the logic is, whenever here switches are there, SAP upper switch for A leg, SAN or lower switch for A leg, SBP upper switch for B leg, SBN lower switch for B leg, SCP upper switch for C leg, SCN lower switch for C leg. Whenever the reference voltage, let's say this A voltage is greater than the triangular carrier, output is high. See, it is from this point to this point, A is higher, so SAP is high. SAN reciprocal of that, SAP is high, SAN is low. Whenever this is higher, whenever the triangular is higher, SAP is low, SAN is higher. This is your normal pulse width modulation. But see, this line is a transition from A to A upper to A lower. So what happens during this transition time? Your A upper is conducting, now your A upper is off and AN has to be switched on. But SAP takes finite amount of time to turn off. So for 4 microseconds, SAP is off, being turned off. SAN is not given the signal. SAN is given signal to turn on, delayed by 4 microseconds. Turn on is delayed by 4 microseconds. Turn off is not delayed. Okay. So this pulse width reduces means your voltage reduces. The fundamental voltage is reduced. This is the dead time. But what happens in Z source? Let's look here. Whenever the transition is going to take place, for 4 microseconds, we short circuit the switches. For 4 microseconds, we short circuit the switches. What happens? 4 microseconds, for 4, that small, I'm not saying 4 microseconds, let's not say 4. That was a constant value I'd use in my practical. This is a shoot through stage. For some time period, small time period, all 6 switches are short circuited. What happens because of this gray area? All switches are short circuited. What happens because of that? The energy will be stored in the inductor during that small time. Motor is disconnected from supply, but because of inertia, motor will keep on rotating. This is going to be some microseconds. So motor will not see much change. But when you remove the shoot through stage, the inductor will supply the energy. So your voltage is boosted. And the DC link capacitor will store this value. So your DC link voltage is going to remain high. This is how shoot through stage are there. The problem of dead time in terms of distortion is removed. Someone will say, okay, shoot through also reduce the fundamental voltage, but that is wrong, because The shoot through stage increase the value of DC link voltage. Thereby, we are able to control the fundamental value of voltage. So how does this work? So ZSI voltage available at the input of inverter bridge is function of the battery voltage plus we have new term shoot through duty ratio. So normally your inverter output voltage VAC is given by M into V in by 2, where V in your battery voltage. In Z source we have one more term B. B is your shoot through duty ratio or boost factor. So how does this work? So VAC is the peak value of voltage here. M is your modulation index. B is your boost factor. V is your battery voltage. So boost factor is given by 1 upon 1 minus 2D. 2D is your shoot through duty ratio. For how much period of time your shoot through state existed with respect to the total switching period. This is T0 is the time for which shoot through state existed. T is the total sampling, total period. Right? So by controlling the value of T0, T is constant. By controlling the value of T0, you can control D. By controlling D, you can control B. By controlling B, you can control AC. So D will be always less than 1. Okay, because D is less than 1, 1 minus 2 into something less than 1, not less than 1, less than 0.5. So because of this, what will happen? This denominator will be less than 1. Because of this, B will be more than 1. If B is more than 1, then we have got boost effect here. So this is the control system for your Z source inverter, propelling an induction motor using Z source inverter is being used to propel the induction motor. The inverter remains same. The control strategy for IFOs is indirect field oriented control, that is say vector control only. Only changes is additional loops. See, you are going to control the voltage across this capacitor. Okay, how much voltage is required? You compare with the reference value. How you got the reference value? You got the reference value based on the motor rating, how much DC link is required, how much battery voltage was there, that much boost factor is required. So you got the DC link voltage here, reference value. So this value is compared with the actual capacitor voltage. Voltage control will process this and say, okay, this much inductor current should flow so that required amount of energy is stored so that these two voltages are matching. Then I compare it to the actual inductor current. Current controller generates D0. This D is the duty cycle, the shoot through duty ratio. So now your SPWM will change in these terms, right? SPWM will change in these terms. So two of my students are working in PhD students are working on Z source inverters for EV applications. So they were having real tough time implementing this PWM modulator because most of our DVSP processors don't have a special function for shoot through. So you need to design a separate circuit for shoot through, and how that shoot through is to be controlled, that is a challenge. So if you want to work, let's say for a small BTech or MTech project, you want to give this design of this circuit will be the main thing. How to design this circuit when you have, we already have circuits for this VA, VB, VC and sine wave pulse width modulation. But how to incorporate this duty shoot through duty ratio, that can be a new thing. Same thing can be applied for your EMSM. This is the same thing. Only thing is we have changed this diode to a bidirectional, means an IGBT, so that the current can flow in reverse direction during the regenerative braking. So people have also reported it for fuel cell. So this is your fuel cell and capacitor and battery they are put here. So different modes are there. In mode 1, fuel cell is supplying the motor. Fuel cell is charging the battery as well. Motor is giving power to the wheels. In mode 2, battery and fuel cell both are supplying to the motor. Let's say fuel cell has less power to supply now, or battery is fully charged and you want to give, both can supply to the motor. Mode 3, fuel cell is cut out and battery alone is supplying the motor. Mode 4, motor is acting regenerative motion, braking and supplying the battery. See, different modes are there, and regenerative is fine. Okay, this mode will remain constant. What about this? Battery, fuel cell, battery and fuel cell supplying motor as well as battery. So different modes are there. Which mode to select and when to select that mode, that is a challenge. You can treat it as an optimization problem, or you can use your ANN and ML machine learning to check. Just like your many of in power system. I'm not great in power system, but when I was going to the faculty profiles in your university, I found quite a few are working in the area of power system. So they might be able to tell that scheduling of different generators we do, we'll add some optimization problem, a Lagrange's problem, put constraints and put some condition that this much cost per megawatt is there. So how much megawatt of that energy should be delivered by which generator under the given operating conditions. Same thing can be applied here. That fuel cell or battery, how much power which should give so that our cost is, we get minimum cost or maximum efficiency. right? So this can be optimization problem. What are the limitations of Z source inverter? I will just cover in short. So your unidirectional power flow, high inverse, discontinuous input current, higher capacitor voltage. So these are the problems. Isolation between there's no isolation between the high voltage and low voltage DC rail. So different power structures are there. So one is changing the bidirectional switch. This diode, we change this diode with a bidirectional switch, and we can get the regenerative braking. But this is this needs a replacement. A separate gate driver is needed. Same way, what we have done here to reduce the starting current, what has been done reported in the literature is that the inverter was like this, it is shifted here, and now you have got your Z or impedance network after at the negative of the DC rail. Your motor connections remain unaffected. So it has discontinuous input current, then quasi Z source ZSI is there, PZSI is there. I just want to take the last point of this induction, this V2G and G2. So I'll just go a little bit. So here you are used. So what I'm trying to say is that the different Z source topologies are there. You can work on different topologies, their control, and one more most important aspect, their PWM generation. How to incorporate duty ratio or shoot through duty ratio in your hysteresis control or space vector modulation. That will be a challenge. And again, topology design. Like one of my PhD student, I told him that he worked on a new topology and came up with a new topology within some 6 months. I was trying to convince him, don't do anything new. Explore this topology, write 2 papers and finish your PhD. So if you are able to develop some new topology, how to develop new topology? You have to just play with L and C. That's all. So you can quickly get your PhD students to work, or those who are working in this area, they can attempt for PhD like this. So last topic I will take over. This is one of my favorite topic, and because it's open to interpretation, lot of scope is there. That is V2G and G2V. So what is meant by V2G and G2V? So it involves interaction between EV and the grid. So you have vehicle to grid. This utilizes the store. What does vehicle to grid do? The energy stored in the battery is used to send the power back to the grid. So your vehicle battery is acting as a source and sending the power to grid as and when required. Grid to vehicle means you are charging your vehicle. You are taking power from the grid and charging your vehicle. So before we started, just let's have a look at the microgrid. This is a standalone microgrid. That means it's not connected to grid. You have solar PV and battery and a common DC link. PV requires a DC-DC converter to employ maximum power point tracking, and battery requires bidirectional because it has to give power as well as absorb power when charging, give power when discharging. So you have common DC link here with a DC link capacitor. Then you have voltage source inverter. All your loads are AC. So this will convert DC to AC for the load. Just for the system reliability, right? Suppose if it's cloudy and battery is discharged, no power will be delivered to the load. So just to have here a diesel generator, just to increase the system reliability, that's all. Undoubtedly, it is going to cause pollution. This is standalone. There is no grid is not playing any role in this. So because grid is not playing role for reliability concern, we have this diesel generator. When we talk about grid tied microgrid, you have solar PV, again VSI, and this is grid. So we have replaced our diesel generator with grid. So we have this point of common coupling where load, grid, and this microgrid are connected. Sources for microgrid, renewable energy, usually solar, because it's abundantly available. Problem with wind is it's highly unpredictable. Solar, even if we don't want, if I talk about Gandhinagar, most of the time it's too sunny. Battery backup is required often, but battery backup is going to incur cost, battery life, battery management system, all this will play a role. Why solar energy free and abundantly available? It's available almost for 10 months or a year, we can say, except for the barring the rainy season. Why solar battery? Let's talk about this. Battery will charges from PV if grid load is not in the position to receive the PV power. If grid or load is not in the position to receive PV power, will charge the battery. Battery discharges to feed the grid or load if PV power cannot meet the demand. This is the role of the battery. Let's take an example. Suppose a faculty is driving to the college at 9 AM, stays till 5 PM timing. He arrives 15 minutes early, that is 8:45 AM. He comes in electric vehicle, parks his vehicle in the college parking lot, leaves at 5:15. What his vehicle does from 8:45 to 5:15? Nothing. The vehicle is not going to do anything in this time. Can we make of this idle electric vehicle from 8:45 AM to 5:15 PM? Can vehicle make some money for us? Can we contribute to the betterment of society? Can we help avoid power cut? Let's try to answer these questions. Okay. Going back to microgrids, what was the problem with the battery? High cost, battery management system, all these things are required. Battery life is an issue. High, and see, you cannot have 10 kilowatt system and keep a small battery. You need to have appropriate size of the battery. So higher the rating of the battery, higher the cost. And we have centralized charging system. See, this is a centralized system. That means, see, battery will be consisting of cells connected in parallel and series. That will make one battery. Many batteries are connected in series. That will make one battery string. Many strings are connected in parallel. That makes your complete battery set. So in one battery, if one cell goes out, that battery is out of picture. If one battery is out of picture, entire series string of battery is out of picture because it's open circuit. Let's say for protection purpose, we have to bypass the battery or open it. If you have to bypass, then you need to have DC-DC converter for each battery, which is again a challenge. So we'll just bypass the entire string. So this is the problem. If charger fails, and if this DC-DC converter fails, this entire battery is out of picture. These are the problems with the centralized system. Let's have a look at a decentralized system. What if we have many batteries at different locations? Each battery has a separate DC-DC charger. Okay, so if fails, only one battery goes out of picture, not the entire string. If one bidirectional DC-DC converter fails, only that small battery goes out of picture. This is decentralized. But if we do this, the number of DC-DC converters are required. Again, more switch count, more reliability, the fabrication of PCB, signal electronics, separate controller is required, right? Your DSP card or whatever you say, FPGA card is required. So all this will incur more cost. This is economically not feasible. How to make it economically feasible? Let's see that. Decentralized batteries, microgrids with reduced battery cost. What are the answer? Vehicle to grid is the answer for this. Decentralized battery means each vehicle battery will be a separate source. Each vehicle charger, that means you come, park your vehicle, plug it into the socket, plug it into the battery, it will start working. So separate DC-DC converter in the vehicle is there. It is plugged into the socket of your parking station or your parking lot. It will try to interact with the parking lot and send the power to the grid. So we can have a microgrid in our university at lesser cost because battery cost is on the user, on the EV user. Naturally, will give some economic benefit to the EV user. And this gives a scope for power trading. Let's say at afternoon, the power tariff is high. So the fellow who has plugged it into the socket, he will be sending the power to the grid. So he'll get some money. The main user, the main charging station gets this station gets the money. That money is divided between different users, depending on how much power they have sent, at what time they have sent. This has a scope for EI in terms of scheduling, plus optimization problem will be there undoubtedly. Plus one more thing is there. Each user has different requirements. Someone says 2 kilometers away, someone says 10 kilometers away. So that AI will be processing whatever, how you are driving that to the cloud. That cloud will keep your data, use ML or AI or some other algorithm to process it, data processing, optimize the data, process it, and tell, okay, this driver usually during this time of the year or this time of the week drives in this fashion. Let's say someone goes every Friday to have food at, let's say, a Pani Puri stall 10 kilometers away, then goes back to his house at 5 kilometers away. So it will find out, okay, this is the driving pattern. It will also interact with GPS and say, okay, this fellow in this time with the, as per the GPS data, this much traffic will be there. So this much energy is required or state of charge is required for the battery. So that is how the trading will be there. Plus, user can override that. User will say, okay, I have some extra work today to do shopping. I'll go into market, additional 10 kilometers. So he'll punch that. So all this will make a complicated problem, which is gives a good ground for AI to solve. So these all things, power trading, economic benefits, microgrid with reduced battery cost, decentralized battery, but higher reliability has led to V2G. So this is our V2G, your battery, bidirectional DC. So many batteries will be there depending on the different numbers of electric vehicles. Okay. So key points for V2G, integration of electric vehicle to power grid. You can also pitch in, see here I have kept solar as well. You can keep solar here as well. So solar is also charging, provided to grid, battery is also provided to grid, and if required, solar can charge your battery. So initially what we said, reducing your reliance on the coal-based thermal power plant. So solar can be used to charge the batteries. Another concept can be at your home. You have driven your vehicle to the college. At your home, you can have a solar station or a solar array which will charge the battery. I installed some 3 kilowatt solar plant or rooftop solar plant. I got a bill as minus 26 rupees. So it's very effective. And here the government was providing subsidy as well. So depending on that, you can go for it. So that solar rooftop can charge a battery at your home. that battery can fast charge your EV battery. So 2 batteries are required for fast charging. So in the morning you are at college, your EV is at college, your EV battery is at college. So the battery at home will get charged. At night it will charge your battery, and it can charge in a faster fashion as well. So that is an added advantage. So key points. Oh, sorry. The charging structure and location. Integration of electric vehicle with the power grid, that will be the key point, how to integrate. So the persons who are working in phase lock loops, second order generalized integrators, and such type of algorithms, they can come into picture. V2G provides electric vehicle owner charging in low load with low electric price and discharging the vehicle in peak load price. Scheduling will come into picture. Optimization guys will come into picture. Owner can make significant amount of money. Techno-economic analysis can come into picture. Requires connection to the grid, so power electronics comes into picture. Communication course to the grid operator and suitable metering. So that time we'll have the smart meters and development of that can come into picture. So what is the requirement for charging structure should be there, location should be there, we can plug in and communicate with the grid, bidirectional energy power flow from vehicle to grid, control of energy, communication between PEV and the grid. So all the protocols will come into picture, CAN bus and all those will come. Intelligent meter, that is smart metering, PV battery chargers. So charging the battery by drawing power at night time when load is low, discharging the battery and feeding the power to the grid at daytime when the demand is high. That can be application that can reduce your electricity bill, even earn money for you. And undoubtedly the incorporation of solar based charging will reduce CO2 emissions. So different types of chargers are there. I have just touched the time limit, so I will stop here. I'll just give you this, those who are working in power quality, because these days I'm spending most of my time in power quality developing a new shunt UPQC module. So I'll just touch this. So you will have a grid, a battery in between AC to DC converter and DC DC converter. So this is a PWM rectifier. But still it may happen that the quality of supply will degrade here. We'll draw some harmonic currents. So here is where shunt active filter, UPQC and other things can come into picture. So those who are working in power quality issues, they can also target this area. So research topics, as I said, vector control. First and foremost, vector control is built in 1970s, but still we don't have a new technique. So you can work on new technique on this to develop. Undoubtedly direct torque control is there, predictive torque control is there. You can do some analysis, quantitative analysis to prove which one is good in which way. Then you can work with PWM techniques always. Now we are working on random search PWM techniques or random PWM techniques where the switching frequency is random to reduce the EMI interference. That can be one of the issues. Then how to estimate the rotor time constant, and how to incorporate energy optimization in your control of electric motor. That can be a research topic. More than that, Z source inverter, try to build a Z source inverter, new Z source topology, how to implement a control system for Z source, how to have the incorporate shoot through in your Z PWM technique, plus how to develop a PWM card for the Z source inverter. What is the role? And as I said, V2G and G2 has limitless opportunities. ANN, machine learning can come at different aspects, whether it's sensorless PD control, it can come into picture. It can come into picture for your PWM technique. It can come into picture for your estimation of rotor time constants, for energy optimization. What should be the value of ID? Even though I said that ID we keep constant, but for energy optimization, we have to predict what should be the value of ID now. Even if we come down, because at low load periods, like vehicle is cruising, that time you can play with ID. So what should be the value of ID and IQ for energy optimization? Tuning of your PI using ANN, and we can even develop a new controller. Let's say something beyond PI controller. We can always look for that. How to incorporate observers, Kalman filters, and ANN with them. Like say in Kalman filter, we have correlation metrics P and Q or any other name you can use. So how to predict those matrices there is, or how to take care of Kalman gain, there where ANN comes into picture. Gain scheduling is there. So these different areas are there which can be merged to develop the area of electrical and contribute in terms of research, in terms of academics, training students, and for students projects. Thank you for your patient listening. I was happy to deliver this talk. I hope this time, whatever 120 minutes or so we spent, was useful for you. It will be useful for me only and only if some of you get back to me or mail or phone call and we discuss about different topics. And if possible, we can collaborate or work together. Thank you very much.
Thank you, sir.
Over to
Thank
you,
you so
ma'am.
much, sir.
Thank you, sir.
Amit San, sir, thank you so much